All right, cool. All right, so hello everyone. Okay, my name is Shen Loh, and this is a very warm welcome to our online colloquium series. Okay, this is our last talk for the lunar year. Okay, so that's why the background. Okay, the year of the cow. Okay, so happy lunar year, everyone. All right, so for those who are joining us for the first time, this online series is organized by our school, the School of Physical and Mathematical Sciences, or SPMS. Its aim is to invite prominent researchers to provide our students with a gentle introduction of the state of the research of them. Okay, and today is definitely no exception. Now, before we get going, let me address a few logistical issues. Please keep your microphone and video muted for the duration of the talk. And if you have questions, you can post them to the group chat. Okay, and it will appear as a transcript. Okay, on Prof. Loh's screen. Okay, and yeah, we'll keep a lookout for it. Okay. In any case, we will address the questions at the end of the Q&A session at the end of the talk. And so with that, let me introduce our speaker for today, Professor Shen Loh. Professor Loh is a math professor at Carnegie Mellon University and the national coach of the USA International Mathematical Olympiad team. His research considers a variety of questions that lie at the intersection of combinatorics, network theory, probability, and computer science. And his work has been recognized by the USA Presidential Early Career Award for Scientists and Researchers. He also dabbles in social entrepreneurship, previously founding the free math and science education platform xp.com, which sees 500,000 visitors each month, and he has featured in or co-created videos totaling 10 million YouTube views. And today, I'm genuinely honored to host Professor Loh. Clearly, Professor Loh is an accomplished researcher and educator, but what impressed me most is this excerpt that I read from Quantum magazine. You see, when Professor Loh was appointed as head coach of the USA IMO team, he informed the Mathematical Association of America, basically his boss, okay, that his goal as a coach wasn't to be about winning. It was going to be, in his words, to maximize the number of trainees that we read about in the New York Times in 20 years. What an ambitious and wonderful goal. Okay, so even though he claimed that his goal wasn't to win, okay, 2 years after his appointment, the USA team achieved a top ranking in the IMO for the first time in 21 years. Well, today is no exception. Well, today is not about IMO. Okay, upon the outbreak of COVID-19, Professor Loh has turned his mathematical attention to create Novit, the first app to introduce a fundamentally different radar paradigm for pandemic control. And today we are honored to have him talk about this work. The title of his talk is A New Approach for Fighting Pandemics Powered by Selfish Incentives and Game Theory. Professor Loh, please.
Well, thank you. Thank you for the generous introduction. It's actually a real pleasure for me to be able to meet all of you virtually and to give this talk, because I have a lot of respect for people from Singapore. My own parents are from Singapore. And so it's always a pleasure to be able to do this kind of interaction. Now, there's something I always like to ask at the beginning of the talk, which is what are the time expectations? Because I remember seeing some advertisement somewhere saying start at 10 o'clock. But I'm curious, is the expectation that we finish and we have also finished the Q&A by 11 o'clock? Or is the expectation that the talk finishes at 11 and then there's a Q&A? What is the expectation?
It's kind of flexible. It's an online talk.
It's flexible, but I just want to know what people usually do.
Okay, so usually we end at 11 and then we have Q&A, and this Q&A usually.
Oh, okay. Okay, so I can play with that time parameter. That's great. Okay, well, now I'm also going to say it's very, very big pleasure to be able to speak about this to mathematics department. But at the same time, whenever I give a talk like this to mathematics department, I have to apologize. What I'm going to talk about today is completely trivial. It is. Compared to all of the work that we usually do in mathematics, that is deep. I enjoy doing extremal combinatorics. Those are proofs. The proofs that I will give today are only like one-line observations, right? But the thing is, because what this is about actually practical application of some mathematical ideas. So I will talk inside this, saying a few things about how maybe some particular angle from graph theory or network theory could help come up with some of these ideas. However, at the heart of it, everything is very simple. And the way that you know it's that trivial is because I think 2 days ago, it was in the ABC, Australian Broadcasting Corporation, ran it on the national news. And anything that you can explain on the national news, Has to be trivial. Good luck explaining number theory on national news. So anyway, to go on to this topic, the principle is all about how would you try to fight some kind of a pandemic. And the history of how I even got into this is a bit strange, because I actually don't do anything in public health. At least I didn't. About 2 years ago, I didn't do anything in public health. I work in extremal combinatorics, probabilistic combinatorics, studying graphs, studying networks, and so on, and studying sets, studying bounds, things that you can prove, induction, you name it. And then somehow I got pulled into the pandemic side, because it turns out that a part of my own history is that my PhD was supported by a certain fellowship, a certain funding program in the US, for which if you get it, you get funding for 5 years for PhD, and you make a moral commitment that if there's ever a moment of national emergency, you'll come to help. And in March of 2020, well, a call came through, a call to action came through to a lot of the people who had been part of this program before, essentially mobilizing people and saying, if you have any ideas, you should do something. And when I started thinking about this, at first I had no ideas, because as a person who works in proving statements about graphs, sometimes our statements are about graphs with very large numbers of vertices, where that number might be so big that it's more than the number of atoms in the universe by many, 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 many orders of magnitude. But then I didn't know what to do. So what ended up happening was the next day. The convenient thing about being a professor is that occasionally you have a PhD student, occasionally the PhD student's about to graduate. So I had this graduating PhD student, and he gave me some of his thesis to read, because as we all know, the purpose of giving your PhD advisor the thesis is to make sure that at least somebody else in the world ever read your thesis. Well, anyway, I got this thesis, and I was supposed to give some feedback. And as I was reading it, I came to the first sentence, actually, as I started to read, of a particular introductory paragraph, and it was about graph theory. And then I stopped and I said, oh, actually, in this pandemic, this is the first pandemic where there are smartphones. Graph theory, you can use graph theory and you can use phones to build a graph. Maybe we can do something here. And then I just took a pivot, and I ended up going off into a totally different direction. And a few months after that, what I'm going to tell you about is that the team that I lead, we accidentally invented a new way to fight pandemics. Okay, now, whenever you invite a mathematician to give a talk, especially if it's pure mathematician, they'll bring a chalkboard. And for me, my chalkboard is over here. So I will start by drawing a few things, and the screen is spotlighted, so you can see that it is the back here. And let me start by saying a little bit about how you usually control a pandemic, right? So usually if you hypothetically had a pandemic, what would you do? Well, the bread and butter way of controlling a pandemic is that you go and find out, oops, just a second, just save this thing, oops. Yeah, so you find out that there's a pandemic, and if there's a pandemic, then what you do is you go and find out there's a sick person, and what do you do? Just to make sure that there are people here, type something. That way I know that there are people here, and then that will be more interesting of a talk to everybody. What do you do? You got sick people. Oh, I see somebody already has typed something. Excellent. So the way this will work is that what you type is going to appear on the screen. Avoid the sick person is a great strategy if you know who the sick person is, right? And as you can see, the way that I'm running this particular talk is anything that you type goes here. And this makes it so that we can all talk about it. All right, so avoid the sick person. Yes, that would be great. But the issue is that you don't necessarily know who the sick person is. And I mean, you guys in Singapore, you were very effective at this. It's a principle of contact tracing. You go and find out who else was around the sick person, right? And you go find all these people. And then what you do with all these people, put bluntly, is you remove them. You take them away for a while. And this is the basic way that you try to control the spread of disease. I don't mean you as in Singapore, I mean you as in the entirety of human civilization for the last hundreds of years. You find sick person, find out who's around them, remove them from the society somehow, and it doesn't spread. Well, this, in theory, should work. If you just do it very effectively, it will work great. But the problem is that it runs against human incentives. Because actually, if you're going to ask these people to be pulled away from the society, actually, depending on how dangerous the disease is, depending on what their lifestyle is like, they might not actually want to cooperate. And so we've definitely seen that governments which are particularly strong have been able to execute this strategy. But even though they've been strong, I also have, in this course of work, interacted with people from a broad range of countries. And there are countries with very strong governments, which somehow cases still leaked out. And it's because, especially in the situation where governments were very strong, and in those cases, they were being brought away to camps, but people didn't want to get brought away to camps. So if there was a person who was actually around the sick person and the government didn't find them, they didn't go chasing after the truck to be pulled away to the camp. They pretended that they were not around the sick person. I'm basically saying that the incentives don't align. And if the incentives don't align, you would hope to maybe have very strong control to make people do what they should do, but that's hard. So we came up with something very different. I'll draw it out here. I also have slides, as you can see, but I want to draw out a few things first because I feel it's a little bit easier to grasp the concept if you just see things drawn out in real time. What happens if you have a graph theorist or a network theorist starting to think about this problem? The first thing is this is not a very good graph. It's too small. So let's think about what might happen hypothetically if there was a bigger graph out there. And actually, we are all mathematicians, or maybe not all, but a lot of us are mathematicians. And I view that one of the big values that we in math bring to analyzing problems is that we are very picky about definitions. Actually, in mathematics, if you define something carefully, then you can prove lots and lots of things based on that definition. If you have a wishy-washy definition, well, then it's hard to really grasp what you're supposed to prove. It's not strong enough. And so here, the key definition is what is an edge? What's a connection? And that's where we made the first change from the way things are usually done. When we conceptualize this, an edge, a connection between two nodes, between two people, means that those two people spend lots of time nearby and often. Actually, already with this phrase, this is different from how Singapore's contact tracing trace together works. This is different from how everybody's contact tracing works. Does anyone know what's different about this? Just so that there's some more chat. I just wrote down how many words. I cannot count. 6 words. Mathematicians cannot count. What's different? In this definition, there's a difference between the definition of my edge and the edge in typical contact tracing. And it's actually a crucial difference. Anyone know what it is? You can type if you want. Ah, something came in. Okay, so I actually get to see everything come in a few seconds before because the system actually lets me moderate if I need to. But you're saying visiting the same locale at different times counts. That's true. You mean in the typical contact tracing that you guys do, visiting the same locale at different times counts. That is true, and that's going in the direction which is what everyone else has been doing. We went in a different direction. There's something else that's fundamentally different. There's a key word inside here, which actually is not present in the usual way that you do contact tracing. Does anyone know? There aren't that many words. There's one difference. Spend lots of time nearby, often. Well, there's got to be one thing that's different here. Okay, so there are a few things. Yeah, I see 2 answers coming in, right? So one of the things is that, it could be lots of time, and also often versus once. That these are both things. I will say, to the credit of everyone else who's been working in this area, the duration, they actually, I think, do take that into account. But our often is very weird. This is weird. I want to say that this is actually, in most people's mind, this is bad. You'll lose connections this way. Like oftentimes people think about the fact that you have a person and they suddenly spread in the one-off interaction. One-off, right? So no often. So I want to emphasize this is very different. So at the beginning, this would be counterintuitive. Why would anyone want the often? We'll see. So now the second thing is I want to just talk about one concept from the graph theory, from the network theory that I'm going to use. I just labeled one of these nodes as U, and I want to use a concept called the network distance. This is just a metric for a metric space. Network distance is just a way of measuring how far apart 2 vertices, 2 nodes are in a network. And the definition of network distance is the smallest number of steps that it takes to go from one node to the other. So in this case, this is a network distance of 1, 2, 3. That's 3 away in the network. Technically, network distance is the length of the shortest path that goes between 2 vertices in the network. If there's no path, you call it infinity. Okay, so that's the network distance. And now these are the 2 key pieces that come together. What could you do with this that could be more interesting than what is going on right now? Well, let me write down a sentence, just because, again, the phrasing is all very important. So right now, the way things work is in the status quo, after there's a reported case, right? For each reported case, in the status quo, what happens? Everybody who was around that case don't need this often. So it's a different graph. It's actually a much more dense graph. And I don't know how they do on the duration. The locale makes it also much more dense. You get many more edges. But for each reported case in the status quo, you notify everybody who was adjacent in their graph. We do something different. For each reported case, at the time of report, at that moment of report, tell everyone their network distance from the case. You don't tell any names. The only difference is you tell the network distance from the case. This is a non-negative integer, positive integer. If it's 0, you would know. So it's, you know it's you, right? So this is a positive integer. So instead of telling people a Boolean, true, false, saying you were around that person before, and now we know that they are positive, true, false, that's what it used to be. That's the status quo. We report a positive integer. Ping, new case. Here's how far away it is. Does anyone know what this can let you do that you couldn't do before? This is the one, like this is where things get interesting. It's like, so okay, we changed the definition of the graph and we changed the action. And as we always do in mathematics, you write down like a different set of definitions, different set of axioms, and you just start deducing. So now the interesting thing becomes, with this pair of foundational ingredients, what could you do? Does anyone see what this could do for you that you couldn't do before? Actually, think of it as the point of view of you having the app. So you are not the government, you are you. Well, now we have this sense imminent danger. I want to be careful about the definition of imminent. You're right, you can use this as sense danger. I want to be a little bit careful about the privacy aspect, which is that it's at the moment of the case report. If the person later, after like 12 hours, starts walking over and becomes near you, no report, no report. This is only at that moment. That's why I'm being so picky. Yeah, what is my current risk of getting infected? So this is a very important word. You see that these people who are putting the comments in are saying getting infected, not already being infected. The difference is called future tense versus past tense. Okay, great. Actually, this thing can even be animated to go and be even more powerful. You, for example, could show this on a chart. Actually, this is just a hypothetical chart. Suppose it was June 3rd, and you can display to people. Here is their chart. This is them. And first, that's degree of connection is graph-theoretic distance for us mathematicians. This is how many cases were just reported 1 away from me, 2 away from me, 3 away from me, all the way out to 10 graph-theoretic distance, 10 away from me, all the way out to 12, okay? And then the value of something like this is you can animate it. I'm going to go and press play, and June 3rd becomes June 4th, and then also it starts to play. So suppose you saw this, and you are watching as the cases are doing this. What does that make you realize? Suppose that you have some kind of a pandemic. Actually, let's pretend that you don't want to get sick. If you don't care about getting sick, there's no point making any kind of a tool, right? So like, suppose that you are in a pandemic that you actually don't want to get. What does this picture mean to you? It doesn't mean that you're sick. It doesn't mean that you're the one who's dangerous to other people, because this is still quite far. But this is where the definition of the graph becomes very powerful. You see, at the beginning, when people look at this, they say, well, look at this concept. At the beginning, a lot of people say the concept is silly because in Singapore, everyone's within 3 degrees of separation anyway. Well, yes, in the graph that everyone else is using. But look at how we define here. What does this actually mean? Actually, for our lots of time nearby and often, we actually, our whole thing is anonymous. It's not like Singapore. Singapore knows who you are. We built this in a way that you don't know who you are. And that's the point. That's the only way you can operate in the United States. But on ours, we are only testing if these 2 smartphones are together on multiple different days. And the durations that they're together, okay, actually, we're all precise here. I'll be very precise. We check to see. Often means within the last 14 days there were at least 2 different days on which something happened. Okay, that's the often. Often means at least 2 different days within the last 2 weeks, something happened. What's the something that happened? Spend lots of time nearby. For us, that just means that the 2 phones were within 5 meters, for at least 15 minutes. Actually, it turns out that that definition is pretty useful. You may ask, why 5 meters? Why not 6? Or why not 2 meters? Why not 20 minutes? Why not 30 minutes? Actually, it's really robust. In that definition, the most important ingredient was 2 different days. Why do we have 2 weeks and 2 different days? It's because sometimes you see the person every weekend on one of the days, Saturday or something, or maybe every Sunday you go to this place, you're always with this person. And we are doing 2 because 2 is not equal to 1. And the point is 1, you get one-offs. With 2, if you think about your own life, which other people are you around with this definition? Actually, I'm curious. If you don't mind typing in, this helps me understand your way of life as well. Think to your own life. Think about your own life. What kinds of people's smartphones were within 5 meters of yours for at least 15 minutes on at least 2 different days, at least 2 different days in the last 2 weeks? How many people is that? I'll answer mine. In my life, it's like, in my life, actually, it's just my family, basically, and my very close coworkers. Commuting on the same bus, that's true if you're with the same people, like on the same bus. I don't actually know how the buses work in Singapore. I know that when I often go to New York City, if I commute at the same time on the same train, my chance of being within 5 meters of that same person is basically not happening. But on the other hand, if it's a bus which is scheduled maybe every half hour, maybe that's what you have, and you always leave for work at the same time, actually it's good. You should be associated with that person. You should know. But you see, the people who are answering, this is actually pretty tight. This is not something that would make Singapore's diameter is length of the longest distance between 2 points. The diameter in Singapore under this graph is not 3. It's actually quite high. Okay, and the reason why then this particular display is useful is because if you have this display, this is suddenly actionable. Because suppose there's a disease you don't want to get, and suppose that disease that you don't want to get reaches down to pretty close to you. Actually, let me switch to the slideshow now. Suppose you don't need to learn about me. Suppose that you see this chart is changing, and the disease is getting closer and closer and closer. Well, there's lots of things you can do, because if you actually don't want to get this disease, well, a lot of people would start to be careful at the distance of 3. Being careful at the distance of 0 is useless. You are already sick. Definition of distance 0 means you are the sick one. Distance 1 is also kind of the too late side. So most people become careful at distance 2, distance 3. And then there are actually things you can do. In the particular variant we have right now, I understand that the way that most countries, including the United States, are approaching Omicron is, well, everyone's going to get it. And so many people are not being super careful because they don't view the lethality rate as something that makes them worry. Okay, but what I care about is not Omicron. Actually, this particular new concept that we invented is potentially very powerful against exactly the kinds of diseases that are the most threatening to the country and to the world. And those are the ones which actually have lethality rate, high lethality rate, and are contagious. Oh no, we're lucky we haven't seen those yet, but we will, probably within a few decades. And suppose there was something that you actually don't want to get, because maybe it would have a high lethality rate. Well, then if you saw something getting pretty close, you would start to do a few things. And the reason why suddenly you're willing to do these things is because it's different from the picture I had previously drawn. Remember, I had previously drawn this picture saying, well, I've got all these people, and maybe these people don't want to be quarantined. But how come all of a sudden you're willing to take these actions? Anyone want to type? I don't know, it makes it more interesting than talking to an empty room. But like, why is it that suddenly here, people might be willing to do something? Whereas in the past, if you only go and tell you, hey, you already were around the one who was sick, you need to go and stay home, don't get anyone else sick. The difference in the motivation that makes it suddenly self-propelled, well, it's because it's for you. I'll just answer that. It's for you. Because suddenly it's something that you can use to avoid getting sick in the first place. So that actually is related to game theory, right? The principle here is about Nash equilibria, behavioral science. The basic concept was we just observed that if you use something like this, like some kind of a tool, doesn't matter whether it's called Novid, doesn't matter whether you make your own in Singapore, it doesn't matter. The point is, if you use this kind of a tool, you actually reduce your chance of getting infected. And you also reduce your chance of getting quarantined, if that's what you cared about, because you could, if you saw things getting closer, you could try to be more careful. Well, the issue is that every other contact tracing app in the world, if you install it, it doesn't actually reduce your chance of infection. Your action to install it yourself, your selfish action of do I install it or not, has virtually zero impact on whether you are getting infected. It reduces everyone else's chance of getting infected, but it costs you something. It costs the chance that you might get quarantined. And then this is where it gets interesting, because the concept of a Nash equilibrium is something that's in this game theory. It's not rocket science, it's trivial. Like I said, everything I talked about today is trivial. But in the Nash equilibrium, the concept of Nash equilibrium is you have a lot of people, and it's in Nash equilibrium. If nobody has any incentive to change their strategy solo, just saying, I changed my mind, I go change the thing, do something else, Nash equilibrium means that on the individual person's basis calculation, they have no incentive to change their strategy. Okay, now Nash equilibria are related to when things are stable. And now it gets kind of strange. You see, because if you compare these two, actually the only Nash equilibrium for the contact tracing app, if it's up to you to install it, of course, if the government comes in and says you have to install it or says you cannot enter the mall if you don't install it, that's different. That's not using standard behavioral science. That's trying to bring in other extrinsic factors. But we're interested in what you can do intrinsically, because that's actually the most powerful. And so the issue is that if you have a standard app which only disadvantages you while helping everybody else, actually, if everybody had it installed and you could do whatever you want, the ideal strategy would be to uninstall it and let everyone else protect you. So actually, it's not a Nash equilibrium at the everybody install point. In fact, the more of the other people that are installed, all the more reason you don't need to worry. And in fact, the only Nash equilibrium of the standard approach is called nobody installs the app. Nobody installs the app, meaning that, nobody installs it, and why would anyone install it? Because if you install it, you're the only one using it. It's useless. This thing has two Nash equilibria. So mathematically, there's already something different between these two approaches. Of course, one of the Nash equilibria is nobody has it installed. Because if nobody has the app installed, you install it, and you have no network to build, so it's useless. So we still have that one. But we have a second Nash equilibrium. Just think to yourself, suppose there is a deadly virus running around that you actually don't want to get, because if you get it, there's a 50-50 chance you die. It's a pretty intense virus, okay? Suppose that you found out that everybody else in Singapore has this app installed. How would your incentive be to install this app? If you know that, first of all, importantly, you know this disease is lethal. You don't want to get the disease. You know that everyone else except you already has the app installed. What that means is if you install it, you get the information from everyone. And you don't even have to wait. It's not like you need to wait for lots of people to install it. Everyone already has it. So you install it and bingo, you get all the information. Actually, the interesting thing here is the more people using it, the more you want to install it. So it actually has a slope. It's actually very interesting. This has a Nash equilibrium. Everybody installs the app, and it's an attractive point. It's an attractor, because the more people who have it, the more you want to have it, because it's going to help you. That's the point. So this is a little like maybe very trivial mathematical angle on looking at this. But the fact that we have gone from one Nash equilibrium to two, where the second one is a stable attractor, and it's also the point you want to get to, this is actually quite exciting. Okay, so if that was the only thing, that would just be theoretical mathematics. But the reason why this is actually interesting is because it has some practical implications, which are quite interesting because they're order of magnitude level. And that's what makes this worth discussing. In fact, I'm very happy that you're willing to listen to this talk and think about this here, because my real goal is just to propagate this concept. I'm not really a businessman. We made this app and then we gave it away for free. But the point of this was we are trying to establish a new concept in everyone's understanding, especially scientific and government communities, that if you ever have a disease in the future that is actually lethal, that people don't want to get, then you should make an app to help them not get sick. That's it. And right now, everybody chose to make an app to help them not get anyone else sick. As a mathematician, we know A minus B and B minus A are different things. Our main contribution is to try to convert A minus B into B minus A. And hopefully by the end of this talk, you'll agree. And here's why it matters, because it has huge impact. The first thing is order of magnitude. It's how much impact this will have in other countries than Singapore. So this particular one is about anonymous. Now, these transmission probabilities have changed over time. And in fact, I only need to say hypothetically what is going on if you happen to have some kind of a disease. I don't need to say this is talking about COVID. But the reason why it's important to build solutions like this is because Singapore is an island, but you cannot survive if somehow the whole rest of the world goes in a very bad shape, because you cannot just keep out the disease. So it's very important that we as the scientific community find the right solutions that work in all countries, especially when the vast majority of these other countries in the world, they required all these privacy things, and they need that, they meaning where we are in the United States. It has to be that whatever you make is anonymous. I claim that there's a problem. When people designed all of these anonymous contact tracing apps, they made a severe oversight. Actually, the history of it is that you guys were first. Singapore went and made these pioneering efforts to use Bluetooth, the Trace Together app. That was great. Singaporean government technology unit figured out that you can use smartphone Bluetooth to do contact tracing. And that is a breakthrough. Now, the rest of the world, a lot of people in the rest of the world did not like the fact that the Singaporean app asked for your identity, your phone number or your resident ID. So the rest of the world said, let's go and make a version of this, which is anonymous. And they spent a lot of effort building the full privacy version, making it completely anonymous so that you wouldn't be able to know who anyone was. And that was kind of a waste, which could have been predicted beforehand. So I live in the United States. I know people who I've talked to who have had these apps, who even told me, one of them told me he had his app and he went to New York, and while he was in New York, the thing rang and it told him, you have already been around somebody who's sick. He had already come back to Pennsylvania by then, and so he was telling me this story. So I asked him, oh yeah, so did you do what you were supposed to do? You know what you were supposed to do, right? When the app tells you that you have been around, you should go and book a hotel room in New York City and live there for a week. Did you do that? Well, you can guess what the answer was. No, of course not. Actually, in the UK, there became something called a pingdemic at the height of the Delta variant, and people just started uninstalling the app because it was pinging them too much, telling them to quarantine. If you think about it, it is completely perverse. It's completely perverse. By the time the app is actually doing something, telling you ping, 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 you need to stay home. And the app promises you that nobody else on earth will ever know you were just asked to stay home. People are selfish. Well, that was kind of a waste. A lot of effort was spent building these things to be, I'm talking about the waste on the anonymous side. The anonymous contact tracing app, people just didn't realize that if you put the words anonymous and quarantine yourself together, it doesn't work. But if you thought about it before you started, you might have figured that out. The second thing here is that, well, what do? We flip it. Flip it to self-protection. Here's where it becomes interesting. Go back to the hypothetical scenario. Suppose that there was this lethal disease running around, which is actually what we care about. How much incentive would people have to actually take caution if their app told them, using the definition we're using, which is very critical? Suppose the app told you distance 2 on this graph, red case, got a definite infection. How would the average person react if it is 50% lethal, and you have just found out a very tangible piece of information? Somebody got positive. That person spends lots of time nearby often, a person, and that person to you is lots of time nearby often. What would you do? What would the average person do? Well, if it's actually that lethal, you would do something. You would decide to stay home, right? And that's because it's actionable. This is why it's different from the loose graph. The loose graph meaning having lots and lots of extra edges. If you found out, if the definition of an edge was looser, and you found out that somebody just tested positive, and it might have been that they went into the shopping mall at some point, and you went into the shopping mall also at some other point on the same day. Sorry, no, not even that. It's like they were in the shopping mall same day with somebody who was in shopping mall same day with somebody else in a different shopping mall, and then you. That is not actionable. So you're not able to use this long distance to do anything. But if you tighten the definition, then it's actually actionable. And once it's actionable, you might do something. And that's where it becomes interesting, because then it's self-driven. Because suppose that you do want to avoid getting sick, because this is this future lethal pandemic. Well, then we've just managed to build the wall again. Remember, the goal was to separate these two sets of people. And the interesting thing is, for the entirety of human history, the way that people try to separate these two groups of people was to try to control the ones who were dangerous. And that's hard, because they didn't necessarily want to be controlled. We said, let the people who are in danger find out how much danger they're in. And the more danger they're in, they'll want to do something. This technique of separating these two people is powered by the same force that at the outbreak of the pandemic caused the United States of America to run out of toilet paper. I don't know if that happened to you guys in Singapore, but in the United States, when the pandemic broke out, somehow everyone decided to buy toilet paper. And we ran out of toilet paper, but we meaning the country. And I'm just explaining that this is an example of how even the government or whoever was saying, stop buying the toilet paper, you don't hoard the toilet paper. The moment the government said that, the government said, stop buying hand sanitizer. Next thing you know, everyone buys all the hand sanitizer. It's because the incentives didn't align. Everyone wants to protect themselves. And you build this system and it becomes suddenly significantly more powerful. That was the point here. Okay, and the reason why we're so excited about this particular piece is because it would work even in non-authoritarian, authoritarian is the wrong word. It would run in countries for which, let's say, the government is not so strong. It would work there too. And our goal is to make it so that if you have something like this well known, then if there is a future lethal pandemic, instead of a mass chaos, you actually are able to control by everyone wanting to control. Oh, actually, here I want to also make another comment about the incentive alignment, which this is this huge impact, by the way, of this different mentality. Actually, just think of it hypothetically. Suppose you have this future disease, 50% lethal, and pretend you are dealing with this in the United States of America, if you can think about it that way, where there's no way that the government is able to go and force a person to do this, person to do that. Well, suppose that you find out. Let's put it this way. How many people would want to be able to find out, like the old-fashioned way, be able to find out only after you've already been around the sick person, at which point you should now go and stay home for like this entire period of time, 1 week or whatever, and there's a decent chance you're actually already infected. And if you're infected, that would be the last week of your life with a 50-50 odds. If you think about human nature, if a person thinks that there's a decent chance that they have 1 week left to live, are they going to choose to live that week in their basement? Unfortunately, no. And I'm just explaining how that incentive is backwards. On the other hand, if you tell someone else, if you go into your basement right now, you will increase the chance that you live more than 1 week. They will. So I'm just explaining that's that particular piece there. Next piece. The next piece is actually very, very important because this is related to the anonymity part. Again, in order for this to be able to work in the broad scale all around the world. And actually, I should also say, I understand that in Singapore, people also care about privacy. And so, for example, whenever we talk to people about this particular innovation, the idea is that, you know, it is possible. You could actually use this too, and you could have something which is both anonymous and helps to protect. And now the key is, the reason why it was so important to be able to have people know, to enforce the identity, was because it would be convenient for the government to just say, you're positive, enter it in, you're positive, enter it in. In many parts of the rest of the world, you can't do that. You can't force them to enter it in. And that actually renders a lot of the other approaches totally dead because they don't even have the signal. We use the triangle inequality to solve this. The triangle inequality from graph theory, or from metric spaces, really, is trivial. Again, it's trivial. So the concept is we are the only ones who decided that there should be 2 buttons on the app. One button says I'm sick. The other button says I'm not sick, but I was around someone else who was sick. And how do you know you're around someone else who's sick? Because there's always contact tracing going on anyway. And so, for example, I will even find out if there's somebody around me who got sick, someone will tell me, some authority will tell me, oh, you were around someone who's sick. We're not going to tell you who it is, but I would know my status is that I was around someone who's sick. Well, what happens if you have two buttons? If you have two buttons, now suddenly you can do very interesting things. Because if you go over here and you think about this picture, if you're able to find out that there's a person at distance x from you who pressed the button saying that they were around someone who was sick. So if we have u is over here, and if there's somebody else whose distance x away, this is this graph theoretic metric, x steps away, well, there's somebody else over here, and what they know is that they are +1 distance from a positive case, a person who's sick. Well, you now know that there's a person who's sick within distance less than or equal to x + 1 of you. That's the triangle inequality. The shortest path between 2 points is the straight path. And if I have an indirect path going here and then going one more to whoever the positive is, right? There's some positive somewhere. Well, it's just going to be at most x + 1. It might be less. It might be like x - 1. It might be x, but it's not far off from x. And now the beauty of this concept is this is still useful for you. Because if what you're trying to do is you're trying to avoid getting infected, well, let's go back to your radar. You get a radar that looks something like this radar. Actually, if you plot on this radar points in red, which are the sick people, and points in some other color like pink, which are the people who just said, I am distance 1 from a sick person, meaning I spent a lot of time with someone who was positive. Well then, if you saw the pink mark, and there was a pink mark right here at 6, meaning that at distance 6 from you, there's somebody who reported positive case near me, then there's a positive case somewhere here, 5, 6, or 7, roughly speaking. Basically, we've just created a signal amplifier, which has the property that whenever there is an actual sick person, the number of opportunities for that positive case to be entered in is actually multiplied by how many close contacts that sick person had. And if they had like 5 to 10 contacts, well, you just boosted the signal by that much. I say it's like an amplifier because amplifiers have a signal to noise ratio. You boost the signal, but there's also some noise. And in this case, the noise is ±1 on this axis. That's not bad. ±1 on this axis is not bad because you're using this axis not really to measure exactly where things are. You're using this to just measure the general velocity of the disease striking closer and closer to you. And if you're off by 1, it's still not that bad. Okay, there's something else also interesting about this, which is that you could have this strange multiplicities. Like what if everybody who was told they were around the case all entered? You'd have a huge stack, like a very tall thing where there's really only one case, but it's very tall. That's okay, because actually all you really care about is the support of this distribution. I shouldn't say all you really care about, but your action, your decision action is usually when the thing got too close to you, if there exists a positive case close enough to me, then take action. Not if there exists 15 cases right next to me, I take action. The point is like many cases far away is not super interesting. What's most interesting is the support of the distribution close to you. And that particular principle, that way of thinking of it, let us see that, oh, great. All we're going to do is we're going to fuzzy up the support by ±1 in this metric measurement. And the benefit is you get to 10x the signal. You get to amplify the signal massively, just based on the fact that you have all these other people entering it. Suddenly, it even works in the United States, because I don't need that 100% of the people go and enter it in. Because even if 10% of the people are nice enough to just press the button saying I was around somebody, well, you've just like 10x'd the signal, right? Because now if each person has about 10 people they're around, and on average like 1 in 10 people actually does what they're supposed to do, it's an existence, right? In mathematics, I want to know that there exists around every single positive case, there exists at least one person who went and pressed it and warned it in, and then everyone else can be careful with a potential error of ±1. This thing is that order of magnitude boost, where the multiplicative factor on that boost is exactly the average number of contacts that the typical person has. So that actually then takes even this anonymous app into the world of it could work. Last one. The last one is what many people say. This is where a lot of people assume that the apps are useless. And that's because all the other apps have this flaw. Ours is the only one that doesn't. The point is that if you have many asymptomatic and untested positive cases, I'm now intentionally standing in front of this, blocking everything. The only thing you get to see is if it's 1 away from you. That's actually how the rest of the world managed all of this, right? It's that you have this app and you only get to find out if right next to you there was already a positive case. Well, if that one was asymptomatic, then you just got hit. That's too bad. And the point is, it's because you have no warning. You have no law of large numbers to use. You have no capability of being able to see using more data to make a deduction. Well, that's why we show more, because now you have the law of large numbers to play with. What do I mean? Well, asymptomatic and untested positive, those two things actually wrap into the same probability. The same probability called, when there's a positive case, what's the probability that it gets detected? Now, if you are only going to talk about it when it gets so close to you and it's that last case before you get it, you are doing a binomial distribution, which is n equals 1, and then this p, which is whatever is the probability you pick it up. That's very weak. But if what I care about is observing that there's a velocity of things moving towards you, actually, if I have a p, which is not 1, but if I can start seeing these cases from farther away, where the n is actually very high, because if you have a disease spreading towards you, if it starts coming in from Changi Airport and infecting and infecting and infecting and infecting, by the time it gets to you, it's probably infected like 1,000 people. Oh, now you have a big blob. And now the law of large numbers comes into play, because if there in truth is some height of n on this bar, and now you have this p that you're hitting against, binomial np. I don't know, are they really independent? Maybe that's not the right way to think of it. But regardless, the general concept is like it should be around n times p. And then you should be able to see that the support has something, and therefore something is coming your way. And then you take action. It will start to become less useful out here where the n is smaller. However, that's again where this comes into play, where it's all about how you want to protect yourself. If you really don't want to get sick, and you know that this thing is losing sensitivity out to here because it's a brand new disease that isn't tested well enough yet, then you might choose to take caution at distance 4 or 5. The analogy is in warfare. In World War II, that's when radar was invented. Wasn't perfect. And so what do? When you see some blob coming towards you, you don't know whether it's planes or whether it's birds. Better safe than sorry, right? Then you go out, you launch your own fighter jet, you go and check, is it planes or is it birds? But at least you had that option. And why I brought up the radar analogy is because once you look at it this way, that's all we did. We just made a long-range radar for disease. And if you have a long-range radar for disease, it is the incentives and the utility of it are exactly the same as radar in warfare. If you have a radar which is not so good at detecting aircraft because maybe the other aircraft are stealth aircraft, so they have a very low radar signature, well, then all the more reason you want to have a longer range radar so you can start to see mysterious blips as that airplane, if it has low radar profile, maybe some angle of it reflects a radar, then you at least get a chance to see some blips before it comes in towards you. And the other thing about this that's nice is because this thing is also scale independent in the sense that if the disease happens to just spread faster, you will simply notice the wave move to you very quickly. In fact, you're just playing a very simple game, the same way a radar operator in World War II and a radar operator today works. Do not get hit. Observe the speed of object coming towards you. If it's coming faster, take evasive action earlier. If it's coming slower, take evasive action. You have more time. You don't have to take the evasive action right away. But that's it. I mean, the point is like if you had something that is not detected very clearly, same as old-fashioned bad radar, then just hopefully get more range on it or take more caution when you see even mysterious things come close. And if the thing is spreading faster, or if somehow it's not even just it's spreading faster, but if the behavior of other people around you is causing it to spread faster because they're not being careful, well, you'd find out, and then you can just make your own decision. In fact, it's like driving a car. You just try to make sure you don't run into the wall, or you just make sure the wall doesn't run into you. You watch yourself driving, you see if the wall's coming too close. If it is, you steer away. And so this concept here is so simple that actually you can explain it to a primary 5 kid. It's just called, it tells you when there's a new case, how far away is the case. And then when it's, and you just don't want to get it to 0. You get it to 0 and that means you got it. That's it. And so this particular approach, this is actually what we came up with. In retrospect, it's actually very obvious. And I guess to sum up this thing, because we're already at the 57, to sum up this particular talk, this is just an example of how looking at everything from starting from a PhD thesis about graph theory, that's how the whole thing started, looking at it from that angle, it was just natural to start saying, what else could you do? Where's a network? And then actually the heart of this particular piece of work was just about that game theoretic element of thinking, if we're trying to solve a pandemic, what are we going to do? Are we going to try to ask people to please do something? Or can we try to cook up some solution which actually has some game theoretic properties, which make it so that even if you're just selfish, it would work? And our hope, my hope of pushing this particular research is that, at some point in the future, within 30 years, we will see a lethal contagious disease. My hope is that by then, the entire world knows the way you need to approach this is you need to help everybody avoid getting sick themselves. Give them a radar. And if there's a radar, you might actually see in all countries around the world a mysterious separation between the people in danger and the people who are dangerous, self-propelled. Sort of like how free market economy works, actually, if you think about it. The basic principle is just make it so that the people have more information to do what they want to do anyway. But if that actually happened, that might actually help to slow the spread of that future lethal disease. And that's why I'm working on this, because it's just rare to, as a pure mathematician, ever come upon something where that concept pushed all the way through to fruition could potentially, not just could potentially, does give a new method that can be used to fight diseases, which is orthogonal, which is different from every other method used before, and maybe, just maybe, could try to control a major pandemic, major lethal pandemic sometime in the future. Thank you. So I'm going to switch to this. Any questions about anything? I just followed your suggestion of talking until 11.
Great. Any questions, anybody? If not, I'll ask. Yeah. So do you have any case studies, or because it's simply anonymous, you have no sensing of? Did they actually? Do you see a repelling of the people? Your data?
Yeah, that's a good question. Let's just go, right? So this is, for example, case studies. It's very weak case studies, I'll say. Okay, a very weak case studies. This is we had some universities which were playing around with this early on in the pandemic, back when people cared more about it, and we don't have any data about people separating apart for two reasons. One of them is because there was no deployment where it was heavily endorsed by saying, hey, everyone go and use this. So it's actually very sparse data just from people exploring around and seeing if it worked for themselves. Oh, I realize I'm not sharing that screen. Okay. And then the other reason is because, as you learned in Singapore, it's quite hard to make iPhones do any Bluetooth communication with other iPhones. As you remember from Trace Together, at the beginning, you had to leave it on the screen. In fact, for us, it was not until December of 2020 that we figured out how to make the iPhones so that they don't need to have the app on the screen and you can still detect. Actually, to our understanding, Trace Together does not have that capability that we managed to figure out. It took significant effort to do some significant programming down in the guts of the iOS operating system. Actually, I was the guy who did that. And that's also kind of fun. I basically read all of the specs. And as all of you who have background in mathematics know, mathematicians are just somehow very accustomed to looking at all of the conditions, seeing, oh, there's a gap here, there's a gap there. That's called how you find a false proof, right? So we eventually found something, and oh, we managed to make it so our iPhone app is able to actually have the phones detect each other even when the app's not on the screen. But that took until December 2020. And by that time, if you think of the history, vaccines came. And when the vaccines were there in November, December 2020, everyone who we talked to said, we have no interest in this anymore. We have a new strategy. Get everyone vaccinated as fast as possible, 2 shots and done. That was how everyone was approaching this. And then so nobody was, pushing these things. So even though we figured out how to make the iPhones talk to each other, there was no interest. However, I can still tell you something fun that we found, right? So case study, I cannot tell you case study in terms of who did we save, how many lives to be saved, but I can tell you something about the emergence of the giant component on an actual random graph. This is actually my area of research also, right? And this is actually showing why this thing was important. as soon as you build a graph for which every user has 2 to 3 connections, you actually get a massive connected component. This actually you would expect. If you have a background in graph theory, or you don't need much background in graph theory, you just need to know if every vertex has 2 or 3 other vertices adjacent to it, well, then it expands, it explodes. It's like a power of 2 type of explosion. It's analogous to a disease, a virus, having an R naught of 2 or 3. Actually, we are just building a viral app to fight a virus that spreads on the same network that the virus spreads. So as soon as our R naught reaches 2 or 3, we're in good shape. But the beauty of this is in a dense community, you don't need much. So if you just need that every user has 2 or 3 other connections in order for this thing to all link up, well, if the typical person in a university setting now, this is university setting, if it's dense and there are around, I don't know, 20 people in a 2-week period who count for this close contact, well, then you only need 10% of those people to be using the app. And that's actually what we saw at Georgia Tech. That's what this thing is. So this is a chart which is not showing how many people are sick, but this is showing how many people are using the app and how far they are from you. And these particular numbers which are here, they go into the hundreds. This was in August of 2020, but they go into the hundreds. And the reason this was interesting is because this chart is something that was posted on Reddit. It's a popular website that college kids just post random stuff on. And it was a Georgia Tech student who was posting on Reddit saying, hey, look, we are connected to 1,000 people. This actually works. And the point of this is around the Nash equilibrium I was talking about. So my point is, we did not have that heavy endorsement, so we cannot say how would this work if we had done it the way Trace Together ran. However, I do know that even without heavy endorsement, we have validated that we're able to have this snowball effect where after you pass this relatively low threshold, you have connected together the graph. And then we tell people, here's how many people you're connected to. And then they start to tell other people, there's 1,000 people connected on this thing. If you install it, you will get the information from these 1,000 other people. And that helps to drive the adoption. That's all we know from case study side.
I see. Sure. Okay, I see. Actually, in principle, you could have run some simulations, right?
Oh, yes, we are doing that.
Okay.
So this is actually that's actually quite interesting. So we are running simulations. In fact, we're working with a group at Oxford. This Christoph Fraser's group. If you have heard of them, they are quite famous. They had the paper in Nature about analyzing contact tracing apps. Christoph Fraser. No, they know their stuff. So they were using open. They built their own software, Open ABM. It's agent-based modeling.
I see.
So we actually built something on top of that. And in fact, the only reason I'm not talking about it right now is because it's still preliminary, right? But I will say it's very, very interesting. It's very, very interesting. And these things can be done in that way. Actually, we have 2 angles of research on that. One of them is simulations. We have another separate angle we're doing with a different bunch of researchers, which is all based on surveys and psychology, and it's in the social science side. Why are there these 2 different angles? It's because the simulation has parameters. The parameters are how much caution a person takes, like what fraction people install the app, and then how do you estimate the parameters, how do you estimate reasonable parameters? You run social science surveys, where the way we're doing the surveys is we're saying, hypothetically, there's a disease that does this. Here's an app, it looks like this. Would you want to use it? What would you do when the app says it's this far away? So those are the kinds of research we're doing right now.
I see. Sure. I think Zhen wanted to say something.
Yes.
Yeah.
Okay, thank you very much. I think the idea for this selfish perspective is very cool. So, but I'm not sure how to ensure the equilibrium will exist. Because you mentioned there will be this Nash equilibrium, right? And then why, based on this perspective, the Nash equilibrium will exist? And that's my first question. And my second question is, I think as you mentioned that this definition is very critical, right? Then how the definition of this often, let's say, is twice per week or is once per week, this kind of different definition will affect the equilibrium. So I'm wondering is kind of how sensitive is the definition of the often in affecting the equilibrium.
Yeah, okay, let's start with the first one. The thing about whether or not, on this thing of like how the Nash equilibrium works, well, our biggest interest is in making an app where when there is actually a lethal disease that people really don't want to get, then it's useful. The way I say it is because if you have a common cold, I don't need to make anything to help you not get the common cold. No one cares. There's no point. There's no reason investing any effort. However, there will be a pandemic X that comes in the future that has 30% lethality rate and contagious. 30% is terrible. Like if something 30% lethal ran through Singapore, you'd be in big trouble, right? So we need a way to stop this. Here's what happens to the Nash equilibrium. That's why I gave the example of the Georgia Tech of passing a very low threshold and then letting you move from one equilibrium to the other. At the very beginning, nobody has the app installed. Nash equilibrium, nobody will install the app. But if there's something sufficiently scary, and if the researchers have all said, this is obviously the right thing to do, and if the government has said this is obviously the right thing to do, and if ABC Australian News, if Straits Times has said, people have been analyzing this thing and saying, hey, this actually makes sense. You will bump very quickly to 10 to 20% early adopters. My point is like this is the story I'm painting. It's that I don't need that the app is installed all the many years between now and that future thing. This app within 1 week, 2 weeks takes flight, right? So now the point is the early adopters will connect the network. That's the first core observation, because the display of the app itself tells you have 5 people that you're directly adjacent to, and then those 5 people have another 25 people they're adjacent to. Yeah? And so the point is, if you get that initial random install of 10%, 20% of the population, suddenly everybody who has the app sees that I have 100,000 people connected to me using this app. At that point, they tell their neighbor, or the neighbor finds out, if you install this app, there are already 100,000 people using this thing. It's actually useful. What I'm trying to say is that the thing that people always think about is, why would I install this thing if no one else has it? You answer the question by having the app explicitly tell you, here's how many people not are using the app total. That's not useful. Here's how many are 1 away from you, 2 away from you, 3 away, 4, and so on. And then you get like the Georgia Tech, the spontaneous, somebody posts on the internet and says, my gosh, there's 1,000 people using this thing. It's gone live. That's actually what I'm trying to explain. The point is that there's the second Nash equilibrium of everyone wants to install. And if you think about it, once you fall down the slope towards the second one, if you passed 40% of Singaporeans having the app installed, all the people who are not sure, if they actually don't want to get sick, they will know I don't need to wait longer. I don't need to wait for it to be installed. It already is there. If I want its protection, I'll be able to have it. That's my point. And why I say this like more lethal thing is that one of the issues with COVID is the lethality rate was not sufficiently high to make people really want to avoid getting it. But if there's a 30% thing going around, I think there'll be very few people who are questioning. So I don't know if that explained the thing about the 2 Nash equilibria. I'm basically trying to say there's 2 Nash equilibria, and yes, you will pass over from one to the other as soon as the average user sees lots of people using it. And that comes from graph theory. It comes from the idea that as soon as the graph I've collected has average degree about 2 or 3, I will get this gigantic linear size connected component, which gives everyone the confidence that we have passed critical mass.
Mm-hmm. Okay.
Yeah, so that's fine. Yeah, and then the second question. Wait, what was the second question?
How sensitive is this definition of offline?
Okay. Yeah, how sensitive? That's a good question. So I know that if you change from 2 days to 1 day, completely different. That's the point. Our point was to go to 2 days, because with 1 day you will have so many connections just from taking the MRT that it's useless, because everybody is within 3 degrees of each other, not actionable. I don't know. We should do some surveys to find out if you change 2 days to 3 days. Again, this is in the last 2 weeks. 2 weeks is chosen because of 2 different weekends, but and I need multiplicity, right? If I change from 2 days to 3 days in my own life, my network does not change at all. I'm just thinking about my own life, right? I have certain people I'm around, I have certain office, whatever, and I'm around them so frequently that over the last 2 weeks, if I go and threshold it at 2 days versus threshold it at 3 days, it's basically the same thing. So that's actually why we chose 2, because the kinds of things that you would miss from 2 days to 3 days are if you, for example, go to church on Sunday, and I did 2 weeks. And so if I only have 2 Sundays, not 3 Sundays in 2 weeks, then I'm not going to catch the church people, right? That's actually why we came up with that number. But at the end of the day, I saw it as going from one day to 2 different days is the major impact. And so that's where we cut it. And then once we cut it there, the next question was, what should be the time duration? What should be the distance duration? What distance amount? And it turns out that's actually pretty robust. It will only become not robust if you draw it down to like 1 meter. Then at that point, that's kind of ridiculous. There are very few people who will put their phone 1 meter from someone else's phone.
It depends on different people's lifestyle, right? The threshold.
It does. And that's why we chose 5 meters. Because for me, 1 meter, if you think about a person's personal space, even when I had other people I was with office in, I will not sit so close to them that my phone is 1 meter from them for 15 minutes. That's just too close, right? So to me, there's this, and actually the reason why we wanted 5 meters is because a lady might put it into a handbag might be on the ground. I personally might put my phone right here on the desk. Already between my desk and the ground, I pick up a meter. And so the thing is that the 1-2 meters, there's some fuzziness. But once you go to 5 meters, 5 meters is long enough that it really is actually catching the people who are in my immediate office area. And so that's how we thought of it.
Okay, thank you.
Yeah, thanks for asking. And the answers to these questions, by the way, it doesn't have to be our answers. I actually don't want this to be seen as just our thing. I'm just trying to tell the whole world a very obvious idea. And there are ways that in a future disease, when I was in Brazil and talking to people, they were telling me about, they want to think about how to use some idea like this with mosquito-borne diseases. Oh, suddenly this is not right. You don't just go based on smartphones being around each other. Now you might actually want to bring in the GPS, and you might even want to start thinking about how, like, are there bodies of water nearby or something like that. So I'm just explaining, like, this is the basic thing I'm adding is just one simple concept called make the app help the user not get sick. Full stop. That's the point. If you make the app help the user reduce their chance of getting sick, suddenly you run into the game theoretic positive, like, good things. But when you only make the app to control the user, it's really hard. That's all. Yeah.
Yeah, I think this idea is cool.
Yeah, thank you. It's also trivial. Okay, other questions?
Yeah. Oh yeah, Tu has a question.
Ooh, there's a question coming in. Okay, not sick. Yeah. Okay, yeah. So if I'm not sick, but I claim that I'm sick, right? So everyone at distance 1 will intend to quarantine themselves. So I'm still free and safe. Oh, so there's a thing here, which is that it is not possible to mark yourself as sick or mark yourself as contact of a person unless you have actually some ticket from the government or some ticket from the overarching authority. The way to think of this is that there are 2 sources of error. One is false positive, one is false negative. The false positive type of error is a person saying, I just want to go and say bad things. That is easier to control. The way you control that is when every country is doing it this way, where there's a government, whoever manages the caseloads, they find out who's sick. They give you a time-sensitive code that you can enter if you wish. But that that's for you, right? And so now the situation is that you cannot just like anyhow do this now. So you at least knock out the false positives. Our main innovation was to help with the false negatives. False negative is called, here, enter the code, and the person says no. In Singapore, I think you have to enter the code. But in other countries, they just say no. And if you say no, that's it. And for us, by having this triangle inequality piece, I have an extra 10 factor of being able to be robust against somebody not willing to enter the code, which makes us more robust by like 10x on handling the false negatives. Other questions? Oh yeah, thanks for asking the question. Oh, I just realized in this way, everyone's also typing it directly into Zoom. So of course, everyone can see all the questions coming. The way I run this, actually, sometimes I do this with bigger audiences and I set it up so you cannot type to anyone except to this chat thing. And when you type to the chat thing, then I can moderate it before it gets up. But here I'm actually just using it because it lets me see on another screen nice big words that show me what you typed. Otherwise, I cannot read. Other questions?
Okay. Actually, I'm still a bit curious. So, like what Zhen said about the thresholds, the magic figures. Is there a systematic way of trying to find out these thresholds given
Yeah,
certain
I think so. I think that the systematic way is called run a simulation. And when I say and actually there's a very specific thing I would be doing with this simulation. It's to figure out what is the difference between 2 days and 3 days, where the primary driver of the 2 days versus 3 days is going to be these kinds of weekly gatherings. You see, basically it's like, and then here's actually, I'm thinking about it mathematically. The point is like, the kinds of infection that will go out through the weekly gatherings, that's like some fraction of the infections that are happening. So it'll have to do with like what fraction of the infections happening are driven by the weekly infections. Because effectively what this tool does is it helps to protect you against infections coming via certain channels. This does not protect you against infection coming randomly at the MRT station, right? We are not looking to make an app that guarantees you protection. There is no such tool in the whole world. We're only looking for a tool which helps you to knock out certain sources of infection, which would be the ones coming along this highway of your frequent contacts as defined by our twice thing, right? So now the question would be, if I tighten it to the 3 times thing, well, then what might happen is I might be able to now be susceptible to infection via the, these weekend gatherings that the thing didn't catch. Mm-hmm. And so that's where the simulation comes in, because then you want to go and see what is the effect of the weekend gatherings. We actually think that the 2 is the way to go. The thing is that the reason that 2 is the way to go is because 1 is useless. It's an integer. From 2 to 3, I don't actually see how there's significant gain from going to 3. It would reduce your number of contacts by some amount, but may as well use 2.
Yeah, this is, I think, also society. I mean, it depends on society. So so that's why I was asking. So given different societies, how do we determine this threshold to use?
Yeah, that makes sense too. I mean, I think the way I would say it is this: if you want to make a tool to protect yourself, right? And think about it back to the radar of a warship. If you want to build a tool to protect yourself, and your goal is to protect yourself against a lethal thing, you actually better safe than sorry. You will want the tool to be more sensitive. So in general, you'll want to set it for the sensitivity, which is as sensitive as possible without you going insane. And the point is, at 1, you will go insane. Yes. 1 meaning if it's just anyone you were around, even 15 minutes within 5 meters at all, within the last 2 weeks, you will just go completely insane. It's not useful. Go insane means that it just is completely red, cannot do anything. So my point is, I think unless that society happens to be so interconnected that the 2 makes you go insane, then 2 is the way to go. Yeah, and then otherwise it's society dependent if it's some other way. Although I will also say, if the society is so interconnected, oh boy, they'll get sick really fast. You know what I mean? Like, it's just, I think if you need to go to 3 instead of 2, you have big problems in the society for other reasons around this pandemic. Yeah. Oh, question. Yeah. Use the whole graph. Yeah, of course. Oh, I didn't even get to talk about that. So actually, the reason why this tool is so interesting is because it's something that in a lethal pandemic, the population voluntarily installs. But what you get from it is vast amounts of information. Actually, there's a precedent for this. It's called the smartphone. It's so useful. I have one. So do you. Guess who gets all the information? Google, Apple, and the United States government. Although US government will never tell you they do. But anyway, I'm just simply saying, like, the way this works is that if you give something that's useful, you suddenly have the opportunity to collect all kinds of things. And I actually wanted to do this to go and collect good things. When I started the whole thing, I said, let's go and build this network and see what we can see. We just didn't manage to reach the point where people cared about this at a point where, But the thing is, if you have a tool that people actually want to use, what I was telling people is you could use this to even anticipate how the variants are spreading. If you knew things like people got this vaccine, that vaccine, you could find out in real time how good is Moderna. You don't have to wait for Moderna to go and run their trials and also be suspicious. Is Moderna trying to say that thing is good so they sell you more? You would just know. You would just know that got sick person, and sick person was around 10 people. Of the 10 people, 5 had Moderna vaccine, 5 had Pfizer vaccine, and statistically, 5 of the ones who had vaccine X all got sick, and the others all didn't. Do you see what I'm trying to say? Like, if you have this information about which vaccine does each person have, when did they get the vaccine, who is sick, my gosh, you could do all of this. And the difficulty was before everyone said, hey, I'm not comfortable giving the data for an app that is only going to tell me to stay home. I have nothing I get from this thing. And if you instead make the app that's useful, well, then suddenly it's just like how you want to give all your data to Apple and Google.
Okay. Well.
Other questions?
Oh, so how big is your network now?
My network, nothing.
Yeah.
No one cares about the thing anymore. No. Well, actually, I should say this. I don't actually know because Carnegie Mellon University has no in-person classes right now. So back in the fall, my network was 200 plus, right? Because there were people in the university who were still using this thing. And actually the way our app is that it doesn't take much battery, so you just kind of leave it there. So I don't know right now because I have not set foot on Carnegie Mellon University campus yet this semester.
I see. Oh, okay.
I don't know how you guys are, but in the United States, a lot of the universities open the spring semester remotely.
Oh, okay. Because of the Omicron, right?
Because of the Omicron, yeah. So actually, I was just teaching like this. This is how I taught my class. Yeah.
I see. All right. So
Great.
I think does anyone has any questions? If not, let's thank the speaker. I think if the speaker is happy, we can always continue chatting. Yeah. If not, I'll stop the recording. Okay. Oh, does it say thank you? Thank you.
Yeah.
All right then. Okay, thank you very much. All right then. I'll end the recording, and those who wants to stay hang around, yeah, feel free to hang around. Okay. All right then. Okay. Thank you.
Great.